All right, anybody else turning in? There's one up here, actually. I think there's staples in there. All right, thank you. Oh, your name? Yeah. It'd be useful to me and probably to you. Okay, thank you. All good, thank you. Yeah? Y'all remember what we were doing last time? Trying to find local max and local mins, right? Local max and local mins of surfaces. And there were no domain restrictions when we were doing that. We were just saying, hey, here's a surface. Find local max, local min, and possibly saddle points, right? And so we figured out what the critical points were. Once we figured out what the critical points were, we calculated D, capital D, for each of those critical points. And depending on what that D turned out to be, it would determine whether or not we have a local max or min. All right, I do not have another mini exam for you today. I'm going to let you just completely focus on the exam, which is a week from today, right? So you have a couple of reviews I sent. Just focus your attention on that. And on that exam, I'm going to allow you to have a reference sheet, okay, for the exam. So you can bring all the formulas that are in Canvas under Files. You can bring any of those. But in addition, I'll let you have one sheet of paper, front and back, 8.5 by 11, standard sheet of paper, front and back. You can write any steps or formulas or procedures on that, but you just can't work out problems. Okay, you can't just like work out a bunch of problems. You can type it up, you can copy, paste, print. I don't care how you put it together. It can be like font 0.02 if you want, right? Whatever you want, but just make sure it doesn't have worked out problems, all right? And that will be allowed on the test. Otherwise, remember we were talking about open book, or we're just going to go with the traditional test with the reference sheets and formula sheets, all right? All right, pardon?
Are we able to use calculators?
Oh yeah, calculators, and yeah, that's fine, yeah. All right, so we went through all these problems, right? Calculating D, and then we finally got to a point where we shifted gears, is where we ended, right? And we said, okay, now what we're going to do is we're going to take our surface, and instead of looking at the surface on its entire domain, right? Instead of looking at the surface on its entire domain, we're going to restrict that domain to something, right? And the restriction of the domain is going to be a closed bounded set. In this case, it's a triangle. Remember, that's the domain on the ground. If you take just those points in the domain, plug them into the surface, you get just a portion of it, right? You get just a portion of that surface. And what we're trying to do is find the highest and lowest points on that green portion of the surface. Okay, we didn't do this, right? So we need to go through the procedure here. So what is the procedure? Here's the procedure. What we're going to do, we're going to find the value of the original function f at the critical points of the function, as long as those critical points are in the domain we're talking about. Look, it's going to make more sense when I do the example, all right? But it's kind of a two-step procedure. First, we find the critical points, evaluate the function at those critical points. Then we have to, the hard part, find the extreme value of the function along the boundary. So how do we move along the boundary? Because it's an infinite number of points. So that'll be the trouble. So let's do this first one. There's our surface, right? And we have a closed triangle with these vertices. I'll go ahead and draw the triangle. I did this last class, but I'll do it again. So 1 zeros here, 5 zeros here, and 1 4 is up here somewhere. We have this triangle. And this is our domain, D, okay? That's the domain. Don't confuse that with the capital D we were calculating earlier. Just calling that domain. So we want to know, if you take just those points, plug them into the surface, right? What are you going to get? What's your highest and lowest points? First step, let's find the critical points. So we want to evaluate our surface F at the critical points that are in D. So that means we need to find the critical points. How do you find the critical points of a surface? What does it mean? You want to know where the partial of F with respect to X is 0 and partial with respect to Y equals 0, right? That's how we find our critical points. We have to set those partials equal to 0. So what is the partial of F with respect to X here?
Y minus 1.
Y minus 1? Partial with respect to Y? We did that, right? I feel like we did do this one, right? X minus 2? Okay. And then we set these equal to 0, right? And X minus 2 equals 0. And we got 1. We got the point 2, 1, right? X coordinate, Y coordinate. Solve those, set those equal to 0. And we said that 2, 1 lives in here, right? So that's in the domain, so I want to use it. I want to figure out what is the value of the original function at that point 2, 1. We did that as well, right? What did we get? It was 1? Okay. Okay. So as a point, we're saying that this point 2, 1, 1 lives on that surface, right? Do we know if that's a max or min? No, we don't. But it's, if there's going to be a max or a min, right, it's either going to happen here or it's going to happen along the boundary. So now we need to do the boundary, all right? So this is where things really get different, like real big shift from what we've seen already here. So when you look at this boundary, okay, this is step 2. When we look at this boundary, we want to evaluate F along the boundary, B and D, around the boundary, right? How do we do that? It's a triangle, right? How do we do that? So here's what we're going to do. Because it's a triangle, I'm going to break it into 3 separate line segments. And I'm going to move along each line segment separately. So I'm going to label this over here. And this doesn't matter what order we go in. In fact, it's probably going to be different than the way I did it here in the notes. I'm going to call this segment from here to here, I'm going to call that L1. That's an L, sorry. L1. This I'll call L, let's go L2 here and L3 here. Doesn't matter, again, you could call those whatever you want, but I'm going to look at those one at a time. So let's look at L1. When we're on L1, what can you tell me about any point, all points on L1, what do they all have in common? The y is 0, right? The y is 0 for sure. So on L1, all points look like this. The y coordinate is 0. And the x coordinate, what can you tell me about the x coordinate? It's just between 1 and 5, right? You know that much, right? Y'all agree? If we're on L1, every point on L1 has to look like that. So if every point looks like that, then what we can do is we can take the original function and we can evaluate it at that generic looking point, right? I'm taking this original surface, I'm saying, hey, what does that surface really look like if I restrict myself to points that only look like x0? And now plug in x for x and 0 for y. What would happen if you plug in x for x and 0 for y? You get 3 minus x, right? And what you're looking at here is more of like a Cal 1 problem. You're saying, okay, what is the biggest and smallest value this can be, right, on this interval? Right? It's almost like just forget we're even looking at a surface. If I walked into a Cal 1 class and I said, hey, everyone, take that function 3 minus x, look at it on the interval 1, 5, and tell me what its max and min would be, right? You could do it several ways. One way is because it's a line, you could just graph it, couldn't you? It goes like 1, 2, 3, and then it goes like this, right? Like that. So because it's a line, won't its max and min happen at the endpoints? Right, at 1? Without any other thinking, because it's linear, I know that this is going to have a max or min at an endpoint. So that's what I'm going to say over here. Over here, I'm going to say, all right, well, look, this right here, right, that's linear. And that tells me that the max min is at, or I should say, are at the endpoints. Are at the endpoints. Which are what? What are my two endpoints? I'd have to replace the x with what? 1. So I'm going to look at this. F of 1, 0, and then f of 5, 0. And what do I get when I plug 1, 0 in? Just replace that with 1, I get 2. When I replace 5, I get what? Negative 2. Okay, so I'm going to start making a list over here. This is not going to be on camera. The first critical point we got from the first part was 2, 1, 1, right? And now we just got two other points. It was 1, 0, 2, and then the other one was 5, 0, negative 2. So far, right, so far, the max looks like 2, right? The maximum value looks like 2, and the minimum value looks like negative 2 so far. But I've only gone around one part of the boundary. Now I need to go along L2 and L3. So I'm just going to kind of do the same sort of procedure. Any questions? Yes, question?
So if we do 2 of them, eventually you won't know the third one right off the bat.
If we do 2 of them.
2 line segments?
If we do these 2, we'll know, oh, you mean the endpoints?
Yeah.
We'll know the endpoints, yes, but we won't know what's happening along this edge, right?
Okay, yeah.
It could be that we get a max or min somewhere in here. Yeah, so we don't just check the endpoints. We have to check the inside. I see what you're saying.
Yeah.
You're assuming that when we go along L2 and L3, it's going to be linear,
Yeah.
right? This was linear. If they were all linear, then yes, it's going to happen at an endpoint.
Gotcha.
But as you're going to see, they're not all going to be linear. All right, you ready to go along L2? Okay, L2. So on L2, all your points look like the x coordinate has to be 1, right? Because you're right here. So every x coordinate here is 1. And then the y coordinate is y, right? It's whatever y is, but y has to be restricted between 0 and 4, right? So now what we're going to do is we're going to plug that into our original surface function with 1 is x and y is y. So replace all your x's with 1s. So 3 plus y minus 1 minus 2y. Y'all getting that?
Yes.
Yes. Collect like terms. 2 take away y. 2 minus y. Hey, it's linear again, isn't it? That's linear. It's linear in the variable y. So if it's linear, we know that it's going to happen at the two endpoints, right? Yes or no? I'm just kind of assuming you're okay with that. Linear, so it's going to happen at the endpoints. End points. So I need to do f of 1, 0 and f of 1, 4. One of those I already know, don't I? F of 1, 0, this is what you were saying. We're overlapping. We've already done this one. So 1, 0, plug that in, we get 2. But we haven't done f of 1, 4. But that we just plug in 4 into this, right? Has the same effect. So negative 2 again? Okay, so far it looks like the maximum value we get is 2, and it happens at 1, 0. And the minimum value is negative 2, and it happens at 2 different places. So far, right? Let me add that over here. I'm going to put 1, 4, negative 2 here. I don't need to add this one again, right? It's already there. Okay, L3 now. I have a stapler right here. Somewhere. Where'd it go? There it is. Yeah. Okay, thanks. I got your text, by the way. Thank you. All right, so third, we're going to go along L3.
we not already assume we have all the points?
How can we assume?
Why can we not already assume we have all the points since we have all the vertices?
You're assuming that the max or min has to occur at a vertice.
I mean, they all are linear.
Well, they've all been linear so far, but they are not going to all be linear as you're about to see.
Okay.
So on L3, right, on L3, what's the point look like? See the difference right now?
Yeah.
Because now you can't say that, oh, X is always this or Y is always this. All you can tell me is that it lives on that line, right? So what I need to do is, I don't want to draw on that picture. I'm going to do it over here. We're at that point here and that point here, right? This is the point 1,4 and this is the point 5,0. What I'd like to do is I'd like to find the equation of this line. And when I say equation, I don't mean vector equation. I mean old school college algebra equation of this line, like y equals mx plus b, right? So how can we find the equation of that line? We need a slope, right? And we need a point slope formula. So let's do slope first. What's the slope of that line? There's different ways to do it, so. Well, the slope is -1, right? The slope is -1. You can do it two different ways. You can go 4 minus 0 divided by 1 minus 5. Did you say -1? Did we say -1? Yes. So slope is -1, right? Okay, and then once you have the slope, you just need a point on the line, 1, 4. There's a point. And then you use the point slope formula, which is y minus y1 equals m times x minus x1. That's your point slope formula. We have a point, we have a slope. So you get y minus y1 is 4 equals the slope -1, then x minus x1 was 1. This is y minus 4 equals -x plus 1, and then just move everything over. You get y equals, let's see, -x plus 5. We in agreement? I don't care how you get that equation, okay? Just you need to be able to get it. Everyone on board? Yes?
Yeah, I know. I get why it's not linear now. Yeah.
You see what's going to happen? So if you are a point, right? If you are some random point on this little line segment, then your x coordinate is x, right? But what's your y coordinate? Your y coordinate is y, right? But that's -x plus 5. So that means that every point on L3 looks like x, -x plus 5. So what I want to know is what does that surface do when you hand it an x and a -x plus 5 for the y coordinate? See, is that kind of cool, what we're doing?
Yeah.
We're just evaluating what that surface looks like restricted to that line. And when we plug in, it's just not going to be as pretty as it's been, right? Okay, this will be equal to, I'm replacing x with x. So I'm leaving my x's alone. I'm replacing all my y's with this. So 3 plus x times -x plus 5, and then minus x, and then minus 2 times -x plus 5. That's the original surface with all y's replaced with -x plus 5. And do you see that it's going to be quadratic?
Yeah.
Okay. Let's keep going here. 3 distribute minus x squared plus 5x minus x plus 2x minus 10. Okay, and then collect like terms, -x squared plus 7x, 6x, 6x, 6x minus 7.
Yeah.
Okay. Now, unfortunately, this is not linear, so we can't say it happens at the endpoints. So again, you have to take yourself back to college algebra, Cal 1, and you have to say, how do I find the maximum and minimum values of a function on a closed, oh, I forgot to put my restrictions, shit, sorry. I forgot to put it in here. What is the restriction on x? We do have a restriction on x. What is it? Between 1 and 5. That is important, okay? Because your x, if we're on L3, the x is between 1 and 5. How do you find the maximum, absolute maximum, minimum value of a function on a closed interval? The derivative, critical. So this is This is the closed interval method from, I started this last class talking about, remember from Cal 1. So what I'm going to do now is this. I'm going to take this right here, okay? I don't know how much you want to act like we're in Cal 1 here, but let's do it. Let's act like we're in Cal 1. Let's just call that function f of x equals negative x squared plus 6x minus 7, and we're on the interval 1, 5, and let's find the absolute max and min of this, right? We're back in Cal 1. So I take the derivative of this, and I get negative 2x plus 6, right? That's for my derivative. Now I figure out where that derivative is 0, and that happens when x is 3, right? Okay. 3, no, it's positive, right? Positive 3.
Yeah. Because it's double negative.
Yeah. Okay. Is 3 in here?
Yeah.
Yes, 3 is in here, right? So once I figure out where the derivative is 0, what I do is I plug that answer and the 2 endpoints into the original function right here. So now I'm going to evaluate. So I'm evaluating f at the critical point and the endpoints. But I'm still in this little problem right here, right? I'm not talking about that. I'm talking about right here. So what is f of 3? What is f of 1? What is f of 5? So what happens when you plug 3 into the function right here? I get 2. 2. You get 2. What happens when you plug 1 in there? Negative 2. And what happens when you plug 5 in there? Negative 2, okay. So where do we have a max? 2, right? When x is 3, right? Okay. So what does that tell us over here? Back over here, right? This is where we were trying to figure out when this is the biggest. This has a max, right? When what? When x is 3? Okay, what does that tell me about the point, though? That's really f of 3, what? 3, I'm plugging in 3, 2. And what should happen when I plug 3, 2 into the original function? I should get 2. I should get whatever this gave me. But let's just double check it. What happens when you plug 3 in for x and 2 for y? Y'all know where this is coming from? The 2, yes? It comes from that right there, right? So just double check that when you plug 3 and 2 in here, you should get 2. 6 plus 3, 9, take away 3, 6 minus 4. Yeah, so it's 2. You get 2 when you plug that in. So I add that to my list over here, right? When I plug in 3, 2, I get 2. And do I have minimum? Yeah, I have it at what? 1 and 5, I get negative 2, don't I? So minimum when x equals 1 and when x equals 5, which really means when I plug 1 in and 5, 1 in here would give me 1, 4, and then if when I plug in 5 into that, I get 5, 0. And do you recognize those two? Those are 2 endpoints, right? We've already evaluated the function there, haven't we? Yeah, so that's it. These are the only critical points right here. This is basically all the information. We've gone along all 3 boundaries. We've looked in the inside, right? The critical point at the very beginning of the problem, and we have determined. That's it. So what is the absolute maximum value of this function?
2.
On that, restricted to that domain? 2. What's the absolute minimum? Negative 2. Now, that happens at 3 different points, right? The max only happens at 1. At 2?
Yeah.
Oh, yeah, sorry, I just looked at it wrong. The max happens at 2 different places. The min happens at 2. Thank you. Sorry, I don't know why I didn't see that. All right, so showing you this visually, right? Visually, that green surface we had, right? That green surface we had right there. We just found that there were 2 maxes. Where are they? Here we go. You see the 2 max points? And then the 2 mins? We found those. All right, let's do another one. Find the absolute maximum minimum values of this function on this rectangle. So I should talk about that rectangle before we get too deep into this. The domain is defined to be all the points x and y where your x's are between 0 and 3 and your y's are between 0 and 2. So it looks like this. Your x's are between 0 and 3. Y's are between 0 and 2. That's our D. That's our domain. You're only plugging those. Remember, that domain lives on the ground, right? Those are the points that get plugged up into the function, and you're restricting your function to just that little patch. What should I start with? What's the first step of doing this when we are trying to find the absolute maximum minimum value of a surface on a closed bounded set? Yeah, we need to get the partials, set them equal to 0 to find the critical points, right? So critical points are first. So I take the partial with respect to x, set it equal to 0, partial with respect to y equal to 0. Let's see if we can do that real quick. Partial with respect to x is 2x minus 2y. That it? Yeah? Equals 0. Partial with respect to y. Negative 2x plus 2. Set that equal to 0. Solve those. Well, this one you can solve, right? This one is what? X is 1? You solve that, that's x is 1. And once you know what x is, you can go back over there and solve that one for y, can't you? Okay. So now using that, if x equals 1, then this becomes 2 minus 2y equals 0. And that means y is 1. So we have one critical point so far, right? Critical point is 1, 1. Is that in our domain? Is 1, 1 in here? You always have to check that. If it's not in there, you're going to throw it away.
Yes.
1, 1. It's here, right? So I do want to check it, all right? So that means I want to take that 1, 1 and plug it into my function. And I get 1. Okay, so let me start making a list over here off camera of what I'm getting so far. If I have an absolute maximum, right, or minimum, it's either going to happen here or along the boundary, right? So far, we've got that to look at. Step 2, I want to go along the boundary. Okay, evaluate along the boundary. How do you want to break that boundary up? 4 line segments. 4 line segments. L1, L2, L3, L4. Right? These should, well, no, it all depends on that. That dictates it. L1, L2, L3, L4. It doesn't matter. I could have, if you like going counterclockwise, go counterclockwise. It's irrelevant, okay? All right. So tell me about the points on L1. On L1, All the y's are 0. All the x's are between 0 and 3. Okay, let's get them all set up. How about L2? All the, if you're over here, all your x's are 0, and your y's are between 0 and 2. Okay, I'm going to run out of space. Okay, L3. X's are between 0 and 3. What about the y's? It's exactly 2, right? Because you're up 2. Right? If you're up here, your y values are 2. Right? And then L4. L4, your x is fixed at 3, and your y's are stuck between 0 and 2. Right? Here on L4, your x's are fixed at 3. And so what you've got to do now is you've got to plug in x0 into that, 0y into that, x2 into that, 3y into that. See what you get. If they're linear, just check the endpoints. If they're quadratic, little derivatives and things like that. You want to see if you can get it? See how far you can get with it. I'll be right back.